Up to this point, we've been writing functions of the form y equals f of x. So we say that y is a function of x, and it's an implicit function of x because you can't see an x here. So if I write the equation, let's say y squared is equal to x, and I want to differentiate this function, I will need to find y in terms of x, meaning I will need to solve for y. In this case, it's easy because I can take the square root for both sides and I can differentiate. And if I take the square root here and I take the square root here, I will have plus or minus here. I will have y equals either positive or negative square root of x, and then I can differentiate this function. This process might not be easy sometimes, so we do what we call implicit differentiation. What we mean by implicit differentiation is basically we're doing the chain rule on y. If we have, for example, y squared equals x, and I want to differentiate this without solving for y, what I do, I'm going to regard y as a function. So let me write it explicitly as a function of x because I know that y is equal to f of x. So let me write it as a function. So I'm going to say this is f of x all squared, right, equals x. Now I can differentiate. And again, you can see here why I am using the chain rule, because I have a function and this function is raised to the second power. So if I want to use the chain rule, I'm going to say this is equal to 2 f of x and then 2 minus 1. Here's the parentheses, and this is the power rule for differentiation, times the derivative of what's inside the parentheses. So what is the derivative of f? I'm going to say this is f prime of x is equal to the derivative of the other side, because I'm differentiating everything here. So I will differentiate the left-hand side and I will differentiate the right-hand side. So what is the derivative of x? The derivative of x is basically 1. So now, if I want to revert back to y, because I know f of x is equal to y, and that's why I am treating y as a function, because it is actually a function of x. And this is how we differentiate if we have a function that is raised to some power. Now I'm going to revert back. So this is 2 times y raised to the first power times y prime, which is also dy over dx, is equal to 1. We know that y prime is basically the derivative of y with respect to x. So I can write this notation or I can write this notation. It doesn't matter. My goal is to find dy over dx, which is the derivative of y with respect to x. That is my goal, or to find y prime. So to find y prime in this case, y prime is multiplied with 2y. So I will need to divide both sides by 2y, and this is by 2y. So I will have eventually y equals y prime, these will cancel, is equal to 1 over 2y, or I can rewrite it as dy over dx is equal to 1 over ty. So this is what we do when we have y embedded in the equation and we cannot solve for y. This is what we do. We differentiate in place, meaning we treat y as if it is f of x, and we do that all the time. Let me give you a different example. So let's say we want to find the derivative for this equation. So to do that, we notice that y is here. Can we solve for y? Yes, of course we can solve for y, but I know if we solve for y, we're going to have a denominator, so things are going to get complicated. In order to avoid that, I'm going to differentiate in place. Again, y is basically a function of x. So if that helps, I am going to switch y back to a function form. So you can visualize that y is actually a function of x. Let's say x cubed plus x times f of x plus 4 equals 0. Now I'm going to differentiate every single term here. So if I differentiate x with respect to x, I'm going to get 3x squared plus I have a multiplication of two functions. So basically I would need to use the product rule in this case. The product rule says, I'm going to put it between parentheses so you're not confused. So I will use the product rule in this case. I will have the first function times the derivative of the second function, f prime of x, plus the derivative of the first function, which is x in this case, 1, times the second function intact. So that is the derivative of this part of the equation. And then finally, I'm going to find the derivative of 4, which is 0, equals to the derivative of 0, which is also 0. Now, I am going to revert back to y and then solve for y prime, or I could just solve for f prime in this case, because I want the derivative of y, which can be represented with y prime, also equivalent to f prime of x, and also equivalent to dy over dx. Those are all the same. So I can leave it like that. Let me actually leave it like that and then solve for f prime of x, because that is what's equivalent to y prime, and it is equivalent to dy over dx as well. To do that, I am going to remove every term that doesn't have f prime and kick it to the other side, and I'm going to leave this term that has f prime in this side. So I want to remove 3x and I want to remove f of x. The 0 and 0, they will cancel anyways. So I'm going to subtract 3x squared and I'm going to subtract f of x. If I do that, I will get, these will cancel. I forgot to subtract it from that side as well. So subtract 3x squared from this side, and I will subtract f of x from that side as well, because I have an equation here. So these will cancel. You will end up with x times f prime of x is equal to negative 3x squared minus f of x. Now, I don't want x times f prime of x. I want f prime of x by itself, and x is multiplied. So I will divide both sides of the equation by x. I will divide here by x, and I'll divide here by x. These will cancel. I'm going to have f prime of x is equal to negative x squared minus f of x divided by x. Now I can revert f of x back to y, and then I can revert f prime of x to dy over dx or y prime, whatever I want. But since I don't have f of x here, I need to put this back as y. So I will rewrite it again. I will have y prime, which is equivalent to that side, is equal to negative x squared minus y divided by x, and that is the final answer. Now, in this case, you might say, why do I have y here? We do have y here because we have it embedded into the equation here. If it was by itself, then I would have taken the value of y and then plug it here instead of that y. But since I have it here embedded in the equation, I don't need to remove it from the derivative. Let me see if I can show you one more example. So I will do this literally without switching back y into f of x. I'm going to remind myself each time I see a y, I have to differentiate a y as if it's a function, because it is a function of x. I will use the chain rule in this case. If I see an x by itself, then that is no trouble. I can differentiate that directly. But if I see y, I have to follow that with dy over dx or y prime, because it's a function of x. So let's do that. So I'm going to differentiate it. Place the derivative of x to the third is 3x to the second power plus the derivative of y to the fourth power. It is 4y to the third power, but I'm not going to stop here. I know y is a function of x, so I have to follow it with either y prime or dy over dx. Let me use dy over dx now. It's the same if you put y prime here. It's exactly the same. Equals, I have a multiplication here. So I have to use the product rule. The product rule says the first function times the derivative of the second function. So the derivative of the second function is 5y to the fourth power. I'm not going to stop because I see a y, and I'm going to follow it with dy over dx because y is a function of x, plus the derivative of the first function times the second function. Now I'm going to make this look nicer by arranging those terms, removing the product here, arranging these terms, and then I will solve for dy over dx. So I will have 3x to the second power plus 4y to the third power dy over dx equals 5x squared y to the fourth dy over dx plus 2xy to the fifth. Now I will bring the terms that have dy over dx to one side, and I'm going to kick the other terms to the other side. So literally I want to remove this term, go to the side that has that term, and I want to bring this term with that term. So in this case, I will subtract 4y to the third dy over dx from this side, and I will do the same to the other side of the equation. So I will have negative 4y to the third dy over dx. Now I will remove 2xy to the fifth from this side, so I'm going to subtract 2xy to the fifth from this side, and I'm going to subtract it from here as well. Now, this is going to cancel with that. This is going to cancel with that. What do I have left? I have 3x squared, and I have negative 2xy to the fifth equals, what do I have on that side? I have 5x squared y to the fourth dy over dx minus 4y to the third dy over dx. Now I have dy over dx here, dy over dx here. I can pull it out as a common factor. So I can rewrite this as 3x squared minus 2xy to the fifth is equal to dy over dx out as a common factor. And then I have inside 5x squared y to the fourth minus 4y to the third. Now I want dy over dx by itself, so I'm going to divide both sides by, so divide both sides by 5x squared y to the fourth minus 4y to the third. If I do that, I divide this side by 5x to the second y to the fourth minus 4y cubed. And I'll divide this side by 5x to the second y to the fourth minus 4y to the third. These will cancel. You will have dy over dx by itself is equal to that side. Let me write it from right to left. So I'm going to flip sides. I will have dy over dx is equal to 3x squared minus 2xy to the fifth power over 5x squared y to the fourth minus 4y to the third power. And that is the final answer. I hope this video helped you understand the concept better.